In this lesson, we'll be going over double displacement reactions. Let's review. In a double displacement reaction, we have compound AB being added to compound CD, turning into compound AD plus compound CB. The way this works is, we can think of the red A and C as metals, and the blue B and D as nonmetals. Essentially what happens in double displacement reactions is that the metals switch their nonmetals. So before, A was in a compound with B, and C was in a compound with D. But after both compounds reacted with each other, each metal had the other's nonmetal. A mistake that a lot of people make is that they write AB plus CD turns into AD plus BC. The AD is right, seeing as it shows the metal and then the nonmetal. The metal always goes first, while for compound BC it is written wrong and it should be written like CB, because in this scenario, element C is a metal, element B is a nonmetal, and metals must always go before nonmetals. Let's look at an example. Imagine we had sodium sulfide, Na2S aqueous plus lead-2 nitrate aqueous. What would this turn into? Remember that AB plus CD turns into AD plus CB, and the nonmetals swap. If this is true, then sodium represents A and nitrate represents D to create compound AD, which would be sodium nitrate aqueous, plus compound CB, which would be lead-2 sulfide, as it's the second metal with the first metal's nonmetal, and it is solid. Now to balance this equation, there are 2 sodiums and 2 nitrates on the left, and only one of each on the right, so if we put a 2 coefficient, this balances it out, and also there are only 1 sulfur and lead on each side. Now this may be new, this AQ, which is aqueous. Different from solid, liquid, or gas, it just means dissolved in water, making it a solution. So this would be a solution of sodium sulfide. This would be a solution of lead-2 nitrate. This would be a solution of sodium nitrate. Visualize it like this. We have the sodium sulfide and lead-2 nitrate solutions in test tubes. If we add these solutions into this flask, the products will be aqueous sodium nitrate, which is this solution, plus solid lead-2 sulfide. Now, unlike the rest of the compounds in this equation, this compound is solid. So the way that we show that it exists and that it's present in this flask is we draw these little dots, which are called precipitates, or solid matter that is insoluble. This helps us to visualize it better, mixing these solutions to get these 2 products. But how do we know that compounds are aqueous or solid? Well, for that, we need to look at the solubility table. For this video, I'm following this chart, but any chart out there is probably just another version of this. Now, how do we read the solubility table? First of all, this top section shows all the ions that are soluble, while this bottom section shows all the ions that are insoluble, and as products, they will be precipitates. So remember, we put aqueous if it's soluble, and we put solid if it's insoluble. Let's look at this column here. For the top section, if the compound has any of these ions, then the compound is soluble, and we would write aqueous. However, there can be some exceptions, which are shown on the right of each ion. So let's say we had iron 2 nitrate. We can see that this compound includes a nitrate ion, so our assumption is that it is soluble. Taking a look at the exceptions, there are no exceptions for nitrate, meaning that any compound that contains nitrate will be soluble. But what if we did have one of the exceptions? Maybe we had calcium sulfate. Sulfate is known to have a high solubility, but one of its exceptions is the calcium ion. Because this compound contains calcium, it is actually insoluble, and so we would write S. The same idea goes for the ions on the bottom, except the opposite. If the compound has carbonate, phosphate, hydroxide, or sulfide ions, then it will be insoluble, except for the exceptions. Moving on. One of 3 things has to happen in order to classify a reaction as a double displacement. there can either be a precipitate produced as a product, a gas produced as a product, or for there to be a neutralization. Let's go over some examples to show these rules. Say we had a solution of potassium sulfate added to a solution of iron 3 chloride. We know that the first metal combines with the second nonmetal, so this potassium will combine with this chlorine, and then we also have iron 3 sulfate. Now let's check the solubility of these compounds. Well, we can see that this compound includes potassium, and also that there are no exceptions to potassium being soluble, so we can write AQ for this compound. But what about iron sulfate? Sulfate is also an ion that is known to be very soluble, and looking at the exceptions, iron 2 is not present, meaning that this compound is also soluble, so we would write AQ next to this. Now, does this demonstrate one of the three properties for a double displacement reaction? It's not a neutralization reaction, we'll get to that in a second. There's no gas produced, and there's also no precipitate produced. In that case, no real changes have happened to either of the reacting compounds, as both their products are still aqueous, which doesn't really help us in the lab. So we would write no reaction, NR. On a test, instead of erasing the KCl and the iron 2 sulfate, put an X through it, showing your teacher that you know that it's wrong, so you write NR next to this. What if we had sodium sulfide being added to hydrogen chloride? Both are aqueous, and they turn into NaCl and hydrogen sulfide. Taking a look at the solubility chart, sodium is a soluble ion, and there are no exceptions to it being soluble, so we can write AQ, showing that it can be dissolved in water. As for the hydrogen sulfide, this is a gas. Careful, do not write AQ. That would make both of the products aqueous, showing that no gas has been produced, no precipitate has been produced, and there was not a neutralization reaction. So it's hydrogen sulfide gas. Now to balance this, there are two sodiums on the left, so we can put a 2 in front of the sodium chloride, but now there are 2 chlorines and 2 hydrogens on the right, and only one of each on the left, so we can put a 2 here to make it all balanced, making this a double displacement reaction producing a gas. But what about number 3, a neutralization reaction? Basically what it is an acid plus a base turning into an ionic compound and water. We won't get into pH in this lesson, but just for your general understanding of neutralization reactions, the scale goes from about 1 to 14, 1 being the most acidic and 14 being the most basic, while in the middle is 7, which is water, the most neutral between acidic and basic. This makes sense as water is produced when we react an acid and a base. But what determines this? Well, an acid is anything with H and then something behind it. So HX is the general formula. For acids, X is a nonmetal. For a base, the general formula is XOH, meaning X hydroxide, and the X is a metal. So let's say we had HCl, hydrochloric acid, which is aqueous, added to magnesium hydroxide, which is solid. Now, just like any double displacement reaction, to find the products, we now swap the nonmetals, and we would first get the H from the HCl and the OH from the MgOH2, and hydrogen plus hydroxide, what do you know, makes water. And water is a liquid. As for the magnesium and chlorine, these group up to make magnesium chloride. Let's check on the solubility table. The halides or halogens, which includes chlorine, are very soluble, and magnesium is not one of the exceptions, meaning that magnesium chloride is aqueous. Now to balance this, we have 3 total hydrogens on the left and 2 on the right. So the way we balance this is we put a 2 in front of the hydrochloric acid, as well as a 2 in front of the water on the right. That way there are 4 total hydrogens, 2, 4 on the left, as well as 4 hydrogens on the right. Also, there are 2 chlorines on each side, 1 magnesium on each side, and 2 oxygens on each side, making this completely balanced. Here's a good question that you can try out yourself. Pause the video if you want to try and solve it on your own, but I'll take it up in just a second. I've even provided a solubility table. If you're able to do this correctly, I'd say you're good with the lesson. Let's read. A solution of nickel 2 nitrate is added to a solution of sodium carbonate. Can this reaction occur? If so, determine the products and solubility and balance the equation. So first of all, we have a solution of nickel 2 nitrate, which is NiNO3 aqueous, plus a solution of sodium carbonate, so Na2CO3 aqueous, and this should turn into nickel 2 carbonate. Remember, A goes with D, and also C goes with B, so this also produces sodium nitrate. Now looking at the solubility table, carbonate is known to be an insoluble ion, and nickel is not included in the exceptions to make it soluble, making this a precipitate in the reaction, so we write S. What about sodium nitrate? Nitrate is soluble and there is no exceptions, and so this is aqueous. So to answer the question, yes, this reaction can occur. We have determined the products and the solubility. Now we just have to balance the equation. It looks like there are 2 nitrates and sodiums on the left, while there are only 1 of each on the right, so we can put a 2 in front of this sodium nitrate. And I believe that all of the other nickels and carbonates are all balanced, so we can put a tick there, and we get full marks. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.